Hi, in this video we are going to calculate the Fourier transform of the signal x of at plus b. Okay. Now, so what is the Fourier transform of x of at plus b? We know that x of t has the Fourier transform x of omega, and we know that a is a non-zero real constant and b is arbitrary. These a and b are real constants. Okay, so how do we calculate the Fourier transform of x of at plus b given this information? That means we know that the Fourier transform of x of t is x of omega, and the constants a and b are arbitrary constants, but a is non-zero and they are real valued constants. Now, we already know the scaling property of the Fourier transform. So, remember the scaling property of Fourier transform, which is the following. If we have the Fourier transform pair x of t and x of omega, x of alpha t is 1 over absolute value of alpha x of omega over alpha. Here alpha is a non-zero real constant. Okay. Also, remember the time shift property of, again, Fourier transform. That means if we have the Fourier transform pair x of t and x of omega, x of t minus t0 has the Fourier transform e to minus j omega t0 x of omega. Here t0 is again a real valued constant. So it seems that the problem we are trying to solve is containing both of these transformations on the independent variable t. That means we have the scaling and time shift operations applied to t. So we have at plus b instead of t. Okay. Now, how can we solve this problem? Now, let us call the signal x of at plus b as y of t. So, y of omega is Fourier transform of x of at plus b, or we can write y of omega as from minus infinity to plus infinity, y of t is x of at plus b e to minus j omega t integrated with respect to t. Okay, now in order to reduce this integral to a certain form, we have to define a new variable. Let t prime be at plus b. Okay, a and b are satisfying the properties we have already defined. That means they are real constants, but a is non-zero. So if t prime is at plus b, now we can calculate t as t prime over a minus b over a, and also we calculate dt prime as a dt. Okay, so y of omega can be reduced to the following form, but first of all we have to distinguish two cases. Now for a greater than 0, what can we say about y of omega? Now y of omega is equal to x of, now instead of at plus b, I write t prime, and we have e to minus j omega. Instead of t, I write t prime over a minus b over a, and then instead of dt, we can write dt prime over a. Now, since a is positive, when t tends to minus infinity, t prime also tends to minus infinity. And again, since a is positive, when t tends to plus infinity, t prime also tends to plus infinity. So the integral turns out to be 1 over a e to j omega b over a, and the integral of x of t prime e to minus j omega over a t prime integrated with respect to t prime. Okay, so this result turns out to be, okay, in fact, we recognize this integral here as the Fourier transform of x of t evaluated at omega over a. Now, this is the case when a is positive, a positive constant. If a is negative, again y of omega can be written as x of t prime e to minus j omega t prime over a minus b over a dt prime over a. However, since a is negative and we have t prime equal to at plus b, when t tends to minus infinity, since a is negative, t prime tends to plus infinity. And similarly, for the upper limit, integration limit, when t tends to infinity, t prime tends to minus infinity. Okay? Now we can interchange the integration limits, and the integral will be multiplied by minus 1. So we can do that and write down the result as minus 1 over a e to j omega b over a. And now we have the integral x of t prime. Now, we have interchanged the integration limits, and therefore we have minus 1 as a multiplier. So the integral is now from minus infinity to plus infinity. X of t prime e to minus j omega over a t prime integrated with respect to t prime. So this turns out to be minus 1 over a e to j omega b over a capital X of omega over a again. Now, these two results can be combined. In other words, this result, which we call 1, and this result, we are going to call this 2. So, combining 1 and 2, the Fourier transform of x of at plus b is equal to 1 over absolute value of a e to j omega b over a, this constant, complex constant, x of omega over a. Okay, so in this case, where we have both scaling and time shift, we are able to calculate the Fourier transform of x of at plus b in terms of the Fourier transform of x of t. Okay, thanks for watching.